right? That's the system every time.
Okay, so there is no agenda here. This is really an informal discussion. I think we're just going to do QA. If no topics come up, I have some topics I'd like to talk about. I'd like you to talk about. Yeah, well.
So do you have a recommended way? What's the easiest way to get this up and running to experiment with?
You can follow the installation instructions and then run, like the example that I gave, save the Zoom energy. That's in the process.
That's the quickest way to get up and running. And then you want to start deviating from that and doing other things. You have to start knowing a little bit more about how it all works.
Okay.
That means the web video.
Yeah, a lot of people at the web hackathon were able to kind of fit their problem somehow into the examples. And
So you can
Were all the hackathon results made public?
Yeah.
By themselves?
so,
Yeah,
Oh,
all the code is open too, right?
I think most of them
Many-
is.
most of them are. I didn't get
Maybe
responses
you didn't
from
get
a
a
couple.
sticker yet.
Should we give out T-shirts too?
Yeah.
Yeah, I'm going to give out T-shirts, and anybody who gives me contact information, email or business card or something, I'll get you an ebook on intelligence.
Stickers?
I think that's going to be better up here. So just speak loudly. We didn't plan for this. One of our mailing list members was like, "Could you please live stream?" You're welcome, Eric.
Okay, so I got a question. I've worked on the OpenHCM thing. They kind of spun off out of the first forums, and we got to a certain point. I'm sure our code was correct. I'm pretty sure it was correct. We had a lot of problems with tuning parameters. I think it kind of fell down.
Was this the old stuff? Or is this
Well, it was off in the white paper. We were on your forums before, and we took the white paper and implemented our own.
So you read your own implementation?
Yeah, yeah. I think we fell down understanding the tuning parameters and how big you need to have the network and coding. It wasn't really about the code. I think we figured the code out, but all this other stuff is really hard to do this development cycle where you test, change parameters, test, because you're talking about spinning up the CLA and running it for a while. How do you deal with that?
As soon as I go for it.
Me?
I'm tired.
Well, we have a number of things, ways we do it. So I mean, let's see. So in your case, you could definitely. We have a number of tests that test the temporal pooler and the spatial pooler in different kind of situations. So learning sequences of different types, overlapping sequences, higher order sequences, lower order sequences, and so on. So I think the first place to start when I keep using OpenHCM.
Well, I think it applies to what.
Yeah, try to port those tests over and see if you can get those working with the same kind of parameters.
Right, and in this world, I've kind of jumped over to the yeah.
Okay.
And so the same thing applies. What's the tooling? How do you test?
Yeah, so we have a lot of tests around that kind of
Yeah.
stuff. And we have an experiment framework which makes it really easy to try out lots of different parameters. So that's kind of what we have out now. And what we do at Grok and Numenta is we have an outer layer which is an automated optimization process. Because some of the parameters are kind of tricky to tune and they're very data dependent. So if your noise is really high, you want your input buckets to be wide, and you want your thresholds set differently, and so on. So we have an outer layer, which is an optimization process that looks at the data and tries out a number of different combinations of parameters to figure out which set of parameters actually works best on the
That's that particle swarm.
That's the particle swarm, yeah, which we have not yet released in the open source, but we do want to. So we extricate it from our product.
So for now, we'll have to come up with our own kind of tooling or workflow.
Yeah, and there's an active discussion going on right now in our mailing list. And I was actually just composing a reply earlier this afternoon on some of that stuff. So I encourage you to kind of contribute to that. We can give you guidelines too. It's not that hard to set up a genetic algorithm or some other optimization process. Not super difficult.
Right.
Is the CLA determined?
The way we've implemented it is completely deterministic, but it does have a random number seed in it. So once you set the seed, it's deterministic. But the randomness is actually an inherent and very critical part of the CLA to create the distributed representations. Yeah. But the code is totally deterministic.
So we can unit test.
Yes, exactly. That's precisely what we do.
But you find interesting things happening many cycles out, and that's hard to unit test.
Well, it doesn't have to be many cycles. It could be for I don't know how big these test sets are, but many data sets wouldn't have to go out.
Right.
Well, we do have plans on adding regression test suite, kind of in probably a separate continuous integration environment than our normal release build. But we have regression tests internally that some of them are probably generic enough that we could move over with a little bit of tweaking. But that's a longer term goal for us.
Yeah.
Do you have benchmarks, performance oriented, across different platforms?
Not across different platforms, I think.
Do you mean against other algorithms or?
No,
Just speed platforms.
Yeah,
We do internally. Not
Yeah.
across different platforms.
I mean, I guess on an Amazon, like we use the 8x large. I don't know if you can move the Amazon instance, but they're one of the higher end instances, and there, with the size of CLAs we use, it's around 10 to 30 milliseconds per inference set, for about 60,000 cells.
is that with learning?
That's with learning. So it's not bad. I mean, it's not super whizzy fast, but it's
Right.
pretty decent.
Is that multi-core or is that
That's single core.
Yeah, I wanted to ask, I think I remember you guys saying something about having contributors be interested in natural language processing. I was just wondering what applications there are of this to that, and if you could talk about.
We were just talking about that today. Well, we've got a lot of people come to us saying, hey, we have this problem, we really trying to understand semantic content in some short amount of text. And there was a gentleman who was talking about this as well. And so this is something we've thought about a lot, but we actually haven't done anything. But we'd love to see this done. I think the CLA would do very well with this. The trick is to get representations of words in the sparsely distributed form. And so we know this one company in Austria, we might have mentioned CEPT. You can find CEPT.at. They read the white paper and they did a system to learn 100,000 words and phrases and built automatically learn sparsely distributed representations of those. So those representations encode their semantic meaning. And what would be really cool is to take something like that and then feed it through the CLA to learn typical sequences of those. But so it should generalize semantically. Then just at dinner, Scott was talking about he has another idea of how to do that. It sounds a lot simpler than what the
Well, I think you could do it with like but it's not speculative.
I mean, speculated at dinner.
Okay.
I don't want to speculate now.
That's not the whole thing. Yeah.
Give the guy a beer.
Latest
Well, yeah.
concept
But it's like,
that creates a concept space, so you can create a concept space with 2,000 concepts, and then threshold the.
but you said there's some existing tools that do this.
Yeah, so there's a Python library, which you can download Wikipedia and use that as a focus for
What's the methodology called?
it. Latent semantic analysis in the search world is called latent semantic indexing.
Oh, latent semantic indexing. Okay, latent semantic analysis. Okay. So that gives you the attributes of the semantics, basically bit by bit.
That will let you choose how many sort of concepts you want to convert your word spacing. So you start with a bunch of words and you have a bunch of documents, and then based on the co-occurrence of words and documents, it creates a concept space that you can convert text into a concept space, which basically is like a value between 0 and 1 for each of the different concepts. So you say you want 2,000 concepts, and you get gives a text, you get a value for each of those. And then in ours, we probably
Well, you just pick the top 2% or whatever, top 5% of the attributes. That's fine. Yeah.
And so it automatically extracts these. You don't have any control over semantics, but based on the corpus, it comes up with its own semantics.
which is kind of a nice property, because if you want to use it specifically for some medical application, you can take a medical corpus
So the gentleman I was talking to earlier today, I said, well, what's the exact problem you want to solve? He says, well, I have some short sequence of text. And he says, I might want to just classify it by the topic. So he said, I would know the topic. So the way you do this, you would train, and he says it's easy for humans to generally do this. So in order to get this, to solve that particular problem, you'd have to have labeled data. You'd have to say, okay, these are a whole bunch of text sequences related to this topic. These are a bunch of sections related to this topic. And you feed these these sentences through. What you should get, you should have the internal representation at the end of this text string will be the CLA's best representation of what that thing is, and then you would just run it through a simple classifier. We've done this quite a lot, and then you basically say, okay, we're just going to classify those internal states of the CLA, and that generally works pretty well. We've done that a lot, and I think that we have a classifier in the source code that's out there now.
Yeah, I think it's KNN and SVM.
So that's a non-biological thing, but saying, okay, it's like reading the internal state of the brain and say, okay, let's just put that in the classifier, because that internal state actually represents everything that the CLA knows about the world and that particular string of text.
It has to know how in the brain it classifies things, do we?
Well, those kind of sparsely distributed representations are built up through the same process, but probably through the hierarchy. So this is a guess that you can shortchange that. It'd be like, you don't actually feed words into the brain, right? We feed sounds and we feed visual patterns and so on.
Yeah, but somehow we were able to like look at something and say, oh, that's a chair.
Well,
So,
yes.
Given that kind of.
So in this case, we're jumping right in saying we have a semantic representation. It's a relative semantic representation of these words. We don't actually have to assign the meaning to what those semantic bits are, although I guess in this technique you would pick. No, you don't even do that. You just have 2,000 concepts. So we don't need to know what those semantic representations, those bits mean, as long as it really helps you understand what we're talking about. You have a sense of what these sparsely distributed representations do. But again, you have these long bit strings where each bit means something, and then you're picking the top representations for that thing. So two representations, if you had two words, they would overlap in certain bits where they have similar semantic meaning.
Oh, I see.
And I could take another word, and it would map a different set of semantic attributes. So the math of sparsely distributed representation says that you can take a word and almost any other word you show it, it'll tell you what's common between those two, and it'll do it in a very sort of brain-like way. So this solves sort of a major representation problem.
I used to, I'm a graduate student at Portland State, and I used to work on a project that worked on object recognition and images, classifying, whether or not there's a tree in the image, stuff like that. I don't know if this would be useful for that, because it's more of a time-based thing.
It actually would be useful. If you use vision, I can talk about vision a bit. So right now, the state-of-the-art vision is a lot of people doing deep learning techniques, if you're familiar with that.
Kind of.
Well, the basic idea that everyone studies, most people study vision, by the way, study image classification. They're not really studying vision. They're kind of trying to classify images.
There's still images.
There's still images, and they're saying, that's not how we see. But even in that case, in the biological distance, it's all about extracting a series of hierarchical representation where you figure out some sort of better feature space, and all these techniques that people use, and there's variations of deep learning. There's HMAX, there's convolutional neural networks, and something like that. HMAX is sort of hand-coded features, but they all work on the basic idea. What you're trying to do is build a sort of a low-level features and high-level features and so on. And then a lot of people say, okay, the way the brain really solves this is that they do some form of what we call temporal pooling. They say, at any point in time, you have an image, and then the image is shifted a little bit. Well, those two images really don't overlap at all spatially. If I took an distance between them, they're completely different. So you can't say those two images are similar, but because they occur in time, you can say that they're the same. And so that's called temporal pooling. It's saying, okay, this plus this plus this plus this, these are all the same thing because there's a continuity in time. Okay. And HMAX does that temporal pooling hard-coded. They hard-coded it. Which is not a very flexible way. Yeah. And then if you talk to people in the deep learning community, for those of you, I don't have any machine learning people here, but So I've had a lot of discussions recently in the deep learning space. They don't really do this well. They don't really have time yet. So what deep learning, which is the current state-of-the-art machine image classification, most of the people in that space will agree that they have to add this sort of temporal pooling. And so they have to add sort of sequence memory, because that's how you do it. You have to learn what typical patterns follow.
Something like a video.
Yes, you have to. The way we learn to recognize images or something is we actually manipulate objects and they're moving in our space, and a child will turn them around and play with them. And this is how we're learning. This is how we're learning that these things are the same, right?
Right.
So anyway, actually, a lot of the CLA was developed with all of this vision in mind. Although I don't think it's a great place to start, because it's in the brain, there's a huge amount of cortex dedicated to low-level vision. It's monstrous, and it just shows you how much memory is involved. We started doing vision experiments with the CLA, and it was taking forever to run.
Yeah.
So,
It is really computational.
yeah, so we think we know a fair amount how it works and how the CLA should work in that space. But today, and we have some people on the mailing list who are interested in this, but it's a little scary for me.
Can you do it with synthetic targets that are simplified so that they can be more readily distinguished?
Yeah.
This is what we were doing.
That's what we were doing for many years. But even so, the space explodes quite a bit. And what we found is we have to do all of these computational tricks to just get things to just even converge in a reasonable amount of time.
Let me explain. It wasn't algorithmically taking a long time. It was just that if you're modeling a large piece of cortical region, it just took a long time for our software to do it. It wasn't like it was a convergence problem. That wasn't the issue. It was just our experiments would take a long time to run. So what we would do is we would cheat a little bit. We'd say, okay, we're assuming that the statistics in this part of the visual field are equal everywhere, and so we don't need to learn them everywhere.
Or was that copying code?
Yeah.
We were cloning. We were basically cloning part of the visual space. We learn a little piece of it and go, okay, boom, 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 boom. But to get that to work right, to get it to all feed into see, there's no divisions here. It's all one continuous thing. So to get that to work right, we did a lot of tricks and a lot of stuff. And we were just pushing the limit of what can be done in software today.
So do you see, let's say we move this to hardware and we get, 1,000, 1,000,000 times speed up, is that doable?
Yeah, sure, obviously. I mean, we'll
so there's nothing wrong with the technique?
As far as we know, I
The
mean,
data
there's
is
a long way
huge.
to go.
Yeah.
Yeah, so this,
we proved it out even for up to, I think, 3 levels of hierarchy that with the CLA you can actually get a lot of the properties that you want. It just took incredibly long time to train and tune the parameters.
we were just spending all of our time just trying to do shortcuts.
So the trick now is to put some energy into encoding so you digest a lot of this.
Well,
Maybe not with
we just moved to other problem
Yeah,
spaces.
Exactly. And other problems, it's the same thing.
Yeah, they're just much smaller.
So
Yeah.
just to give you an example, I've said this many times, but in the actual physics, your cortex, there is a huge amount of stuff dedicated to low-level vision. It's far, far greater than the total space dedicated to language. The language areas are quite small. Actually, language is much, much easier than low-level vision. From the cortical tissue memory allocation space. Because what's going on in the low-level visual space is you're basically having to learn all these invariances over a large sensory array. But once you actually get into the language regions, there's no topology anymore. It's just, you're just learning sequences. Where in the beginning of the visual space, it's just got this monstrous 1,000,000-bit field coming in and it has to be.
Something like 40 or 50% of the neocortex is involved in vision in some way.
Substory, yeah. And I think V1 and V2 are like, themselves are like 20% or something. Those are the first 2 levels.
And then auditory is similar?
Auditory is small. I don't actually know the numbers on that, but vision dwarfs everything. Everything else.
You tried with any budget?
Some speaker ID stuff.
But that was the old stuff. That was the old option. I don't think we've done anything with the CLA in speech.
Yeah. That'd be cool.
Yeah.
So maybe somebody can make an encoder and put it up there.
Yeah.
Yeah. Slice things up into spectrum and then
You have to mimic the cochlear.
Yeah, exactly.
So CLA would be compatible with running on some of these multi-GPU type boxes that use processor packing to get additional speed.
Okay.
Yeah, I mean, we run on normal CPUs just fine.
Right.
The thing with CLAs is that the structures and the information is very sparse. And so to do all our optimization to get that 10 millisecond speed up, speed, we have to do a lot of sort of sparse data structures. The problem with GPUs that we've seen is that sparse stuff doesn't always translate well into GPUs because you have a lot of indirect addressing and things like that. But still, conceptually, I think it's possible. It's going to be.
It's really hard. I looked at trying to do this in a GPU, and I kept running up against every clock cycle in CLA. You end up with a different data structure in essence. I mean, these things map differently, and the GPU is built for video, which is basically that's really easy.
We actually haven't done this, right? But we talked to a lot of people about it, there's sort of a wild ass guess that says maybe the GPU might speed it up by a factor of 2 or 3 or something like that, but it's not going to be a factor of 100. And it wasn't worth it because we can do other things to speed things up.
I think like a FPGA implementation or something where you can really create custom circuits that are really designed for the CLA could get massive speed.
So here's something, I can talk about this because there's a group at IBM Alberton Labs who wants to build custom hardware for the CLA. And their first task they're taking is to implement it on a GPU. And the goal there is actually just learn the issues about what are the problems, what are the difficulties, where are the bottlenecks, and it's not to do something commercial. So that's their current plan, and they're going to go through with that, and hopefully they'll share all that, the results and what they learned from that. But even there, they had to hire someone who's really specialty is GPUs. Apparently it's a specialty that some people know how to do. You need a lot of experience.
My problem was getting the data on and off the GPU every cycle, and then you just lose everything, the bandwidth going from the CPU to GPU. So the only other way to do it would be to actually run the whole CLA in the GPU.
That's what
That's what you want.
That's the whole thing, yeah.
So even there, you have to really worry about sparse structures
and coordinating that GPU processor with all the others.
So we actually don't know, but the super point says there's some reasons why it's just not going to speed up by a factor of 100. It'll be tricky and will be less than that.
How do you feel the process that you put together matches up against Prolog and that, because it's a deterministic process as well? Do you feel like Prolog follows a pattern that is brain-like in any way, or
Prolog is just a programming language, and it's doing first order predicate calculus and the stuff, which is, I guess it's logical reasoning, so the brain can do logical reasoning, but the process is nothing like what's going on in
the cortex. Coming to the same conclusions, it's accurate or not, or found that it's Prolog can be proven to be inaccurate sometimes.
I guess maybe I don't understand that.
Well, think expert systems.
Yeah.
This is sequential language, whereas the CLA is a statistical based kind of connection.
Well, Prolog, you're programming in the inference and so on. Right? Yeah. Well, this is a learning system, right? It's a memory system, and you have to train it.
Well, the Prolog comes up with conclusions based on ties that aren't necessarily obvious.
Well, I guess there's a sort of there's a somewhat of a schism in the world of machine intelligence and AI, perhaps. Many years ago when I started this, hardly anybody thought that studying brains was the way to build intelligent machines. I ran into lots and lots of things. Now there's quite a few people who are interested in this. But it's really kind of two different worlds. Either you go for the traditional AI world where you say, okay, well, we can code up these rules, we can do all kinds of stuff, we use tools maybe like Prolog to do this. Or you can just go, but I don't think you're going to, those two worlds aren't going to bridge together. I think they're really separate approaches. And it's not to say you can't do something very useful in Prolog. I probably can. But it's not a machine learning, I don't see it as a machine learning technique, and it's not a way of building something that learns about the world and from a sensory data stream. So I don't know how to take it further than that.
Okay, another question, sorry. Was related to probabilistic approaches. Do you feel like the brain works in probabilistic way sometimes, and whether you've thought about approaching it that way? I just wondered if that was part of your
Well, if you followed Numenta for a long time, going back to when I first started the company, and we had another co-founder who's no longer with the company, and that was really his approach. He was sort of thinking about these as Bayesian belief propagation type of problems, and we moved away from that. And but you could take the CLA and you could think about it if you wanted to in terms of probabilistic terms, but it wouldn't be a mathematically concise or I don't know what word I'm looking for. We're not solving Bayes equations anywhere. But you can look at a sparse distributed representation is in some sense a probabilistic interpretation of that if you wanted to, but not in a strict mathematical sense.
Yeah, there probably is some way to construct a probabilistic theory around it. We haven't been able to. When we were doing the old way, we kept running up against various obstacles, and the theory didn't really help us. And it was, it's kind of interesting. The breakthroughs came in modeling the biology much more closely, and that's what led to a lot of the breakthroughs. And at some point, I think the theory will catch up. But there's a number of things that are just difficult to do with probabilistic theory and statistical theory.
Some people look at our work and they're very mathematically minded, and they'll say like, well, what is the mathematical formalism for this? And there isn't one today. And it's not clear how hard, when we'll get there, whether you can get there. I mean, it's a complex system that we understand how it works. You can see why it's going to work, but it's not so easy to say, okay, here's the equations that describe exactly what it's doing. I mean, computers are like that too, right? We don't really have mathematical formalisms for code rewrite in CPUs. In the very beginning of the computing era, people were trying to do that. They were trying to figure out would computations finish, and there was the whole computability issue and algorithms discussions, and that dominated the very early, in the 40s, the early efforts in computing. But we moved away from that. We said, oh shit, they work. Let's just program them,
Well, from a black box approach, it's hard to choose whether you want to throw hardware at it or software. And I know that you're not just hardware with UPIC, but I wonder in some cases how to pick it over another.
Another what?
Well, another approach. So if I'm looking at Bayesian networks or something like that.
You'll have to come to that conclusion on your own. I mean, what we did is we had a pretty big list of requirements we were trying to solve, things we knew that we had to solve, the brain had to solve, and it just became impossible to figure out how to do that in other approaches. And I made a list of these things recently. So we had a set of constraints we were trying to solve, and we just weren't able to do it. Maybe someone else could. But then when we went back and looked at biology, it all came together beautifully. And from the perspective we have now, it's hard to imagine those two worlds coming together. That is, that you could solve these things in those other ways. I was trying to get that in my talk today, for example. I had one little moment where I talked about how this stuff is happening in a distributed fashion over the entire cortex. And because I was in a discussion a week ago with someone who's a neural network person. He said, oh, I can run sequences of neural networks. I know these things. He said, I use a recurrent neural network for this type of stuff. And I was trying to get, and I started going through the list of things. Well, it has to be online learning. It has to be variable order sequence memory. It has to be distributed. And when I got to distributed, he said, oh, yeah, that's all right. Because it's not a singular thing. It's not like one little thing that does something. It has to work across a sheet in the brain. And that's what's going on in B1 and B2.
Jeff, can we talk about hierarchy a little more? I read the CLA white paper. Maybe I'm misreading this, but it seems to me that for an input during you're putting in about the same number of bits that you're getting out, right? Maybe I'm reading that wrong.
Or maybe, okay.
It could be more bits than that's fine too. It's not a compression scheme.
Right. Because
it's a pattern recognition.
That should actually have to happen. Remember, you got 1 million bits on your optic nerve, but leaving V1, I think it's more like 10 million. So that is not a compression in that sense.
Right.
But now it's in a different, more useful representational space. And then it does converge as you go up. Then you just start getting. But actually, in the brain, you'll see like vision. It gets a huge expansion when you go to V1, a little bit of expansion when you go to V2 over V1. Then it starts getting a lot smaller than before. The team is already smaller. But anyway, I don't know if you had a specific question about hierarchy.
Well, so, I mean, I didn't see really guidance on the size of the input string that you could put into, you know, your 2,000 column, you know, 60,000 cell HTM. And, you know, but I can see that you're getting, you know, 2,000 bits out essentially with, because you're ordering together the predictive states and the active states, right?
Yeah, actually, it is. All right, we can get into real detail, but if I were to build, let's just start with the hierarchy. Hierarchy is obviously very, very important in all biological systems. We are not modeling hierarchy today. As we said, we were starting to do that with the vision stuff, and then it just got too computationally expensive. And then we decided, hey, look, we figured out that even a small region of the CLA actually can do something pretty useful. So they said, let's go with what we've got, you know, as opposed to fighting battles we can't win right now. So, so we're not doing anything like that. There's nothing in the code about this. There's people want to do that. We want to do it too, but we're not doing that today. So, and therefore, since it hasn't been tested extensively, you know, it's unknown territory. We have concepts that we think we know what it has to do in some ways, but it's definitely a researchy topic right now. But again, it's not a goal that the output has to be compressed. In our region, depending how you look at it, you're going from some smaller number of bits. The way we use it now might be just a few hundred bits, and the CLA actually has 64,000 cells. In theory, in one way of looking at it, you have a 64,000 bit output. Which is fine actually. It's not a problem right at that moment in time. But it's not like you have this. The goal is to make predictions and to be able to detect anomalies, and if you were to use it in a hierarchy, then it eventually has to coalesce, but at the moment it doesn't have to do that.
Isn't a hierarchy though just as simply, I mean, I could take two CLAs running with, you know, input set A and input set B, and then take the predictions out of those and just run it into another one?
You could, but if you're doing something like vision, it's not like that. Vision, you can't just take different parts of the visual space and just parcelate it up. It's a one continuous process, right? So it's a continuous distribution across this. You can't take, you know, this little part of the visual space and just put them into separate CLAs. That won't work. It's a sheet. Just want to clarify about that.
But you could have lower level CLAs that understand, you know, basically
you
line oriented.
Actually, you could, but you wouldn't. It would be very hard to do that if you were saying, okay, this part of the visual space is continuous. So let's take something else. Like your ears and your eyes have separate hierarchies, and then they converge. They start merging stuff like 4 layers up in the hierarchy, right? So they're their own little hierarchies, and then they start combining. So I think as I wrote about intelligence, conceptually it's the same thing happening everywhere. But let's say we had one little region over here looking at one thing, and we have another thing looking at something else over here. So this is some sensor A, and this is some sensor B. Right. It's not like part of the same sensory space. Right. Then in theory, you could build a small hierarchy. Okay. You could do that. That would be maybe a practical thing you could do today.
That's what I'm thinking. I'm not thinking vision.
Okay. Yes, that would be a good experiment to work with today. You could have essentially maybe 3 times the processing power needed that we run at the moment. Because let's say I have a 2,000 column CLA and another 2,000 column CLA, and I convert them to another 2,000 column CLA. So that's 3 times what we got today.
How do you see prediction? Can we send?
You know, I can speculate here. There's a ton of stuff we don't know about how the hierarchy works, and we do know that there's massive feedback. And I have a theory about what that's doing in terms of motor behavior, but I have a little bit less of a theory about what's going on in terms of prediction. And you know, I just
feedback prediction.
Feedback prediction.
Yeah,
it would be. We sit around just a couple of us with beer, we could talk about it. But with 2 cameras running, I think it's a little speculative to guess at that. We do know it's. We have some ideas about some of it, but it's a research topic. There's no question. By the way, one thing you should know that in like Envision, for example, we know that you can actually do an inference on an image in the brain where there's no time for feedback to play any role. So there's the time it takes for you to actually make the inference, there is not time for a single level of feedback going on. But that's probably not true for learning. During the learning process, you probably have to have that. You probably have to have the motor behavior and all this other stuff. So it's probably requires all that.
We're going to have been talking a lot about saving train networks. It's standard. I'm not even sure how.
Yeah, there's a save method right now.
Yeah.
So, and then the model factory and the load from checkpoint. So you can do it now, but there's a combination of pickling and manually writing the files from the C++ code.
And then settings, you would probably also pack those too. Along.
Yeah,
Let's say I want to give my train network to somebody with the settings.
Yeah.
Say, here's my input sensors. I've done it for 2 months. It's really smart.
Do we compress it to anything?
I don't know.
Yeah, I mean, eventually you can choose that.
Yeah.
I thought we compressed it anyway.
Well, it's a sparse. It's a sparse representation that's saved, so it's compressed and that's.
I mean, there's some time to unpack it, right?
Yeah.
It's not just
I don't
job.
know. But the nice thing is, because we're using this in our commercial product, it's fully backwards compatible. So you can serialize the model, save the model, send it to your friend. If they're using a newer version of the code, it'll still work.
We serialize the encoders as well, all the encoder parameters, all of that's
Through the same method. So do you see that as maybe becoming a standard going forward if there's, or is this just kind of an ad hoc way to serialize right now?
No, I don't think what we're doing can be a standard because it's very Python specific.
Okay.
So I think you would really want a language independent mechanism. So we're relying on Pickle a lot, which is Python specific serialization. So I really think you need something that's language independent. And if there was, maybe we can participate in that or something, but we could switch to that. But
I think there are people interested in doing that, and they're on the forums, so maybe we can keep moving that forward. Because I think one day it would be useful to have a standard because you're going to want to share these train networks and interop. So
That's a good point. I don't know thought about that.
well, I think you did. I think I heard you in the lecture talk about distributed hierarchy.
Well, that's not the same as sharing. That's not quite the same as sharing. I wasn't thinking about sharing at that time. I was thinking just that ultimately someday we'll have these hierarchies that the individual nodes don't have to be co-located and they have to be.
that's true.
Right.
Yeah, like vision networks, for example, that takes a lot of time.
It's hours now, but it could be months.
Yeah.
Years.
The other thing we found is it's important to say there's also the dynamic state, not just the static state. So this is sort of the cells which are in predictive state right now. And that's important if you want a system to be able to deserialize and pick up exactly where it left off.
Yeah, but if I was sharing it with someone saying, hey, this system has been learned on X, Y, and Z, and you're going to stick it in some new data stream, then you don't have to, then you don't need to say that. But if you're just like stopping for the moment and want to pick it up again later, then you have to say this thing.
Excuse me? So you were just talking about the difficulty of dividing up the spatial domain. So, but have you looked at dividing things in the frequency domain? Because there's a lot of evidence that the early visual processing systems, those things travel frequencies. You have optical illusions where in low frequency, low visual frequencies, you can see something that you can't.
I don't think the retina does any frequency movement.
So,
There are cells and
so let's
filters in the cells
so
that
like,
recognize.
So I guess where is it in the neocortex or is it in the retina? In the neocortex, it would be learned. Right? So it should be learned from the.
No, in the retina.
Okay, so the general philosophy here we have is like the cortex is a generic learning algorithm. Just incredible amount of evidence to suggest that's true. But the individual sensory organs on an animal like us are quite highly evolved, and they do lots of things. The retina is actually 3 different sensors, sets of sensors. Your skin is like 4 or 5, so these sensory systems. And so what you start with obviously will impact what's learned. But if you come up with a better sensory organ, if you came up with a better retina, then the cortex would have an easier job. Theoretically, evolution has picked the best it has been able to find so far, and we have a pretty sophisticated sensory organ for vision. But so maybe you could encode anything. You can code anything you want. You can create a custom sensor for any CLA that says, I know magic sauce here, and I know what to do here. I can freely do all these things and pre-code it. If you think about, for example, in vision, you go right from the retina, pretty much to cortex. There's really nothing else with the processing. But if you think like audition, there's a whole, I mean, here, it goes from the cochlea to a whole bunch of other things in the brain first, inferior olive, superior olive, a whole bunch. So there's a whole bunch of processing that goes on before the cortex gets to look, to see the kind of sounds. And so they, that's a highly evolved thing. So all I'm just pointing out is, maybe encoding frequency domains in the retina is great. We're not thinking about that. But, you'll to do vision, you'll have to have some sort of sensory organ. And it could be as simple as, some sparse bit graph or something, but the brain is sort of more sophisticated. I don't know.
We haven't tried it, so.
Well, we did try Gabor filters.
Yeah, I was interested in that.
Yeah.
That's a decent. Those. We tried those.
I don't know.
They're good. I mean, they're
There's at least one Gabor file.
Well, there is. Yes.
Okay.
There probably is that same.
Well, then it
It doesn't work, but.
No, I mean, okay.
And what that'll do is give you the edges of things that make up that image.
What's important is when you leave, whatever the sensory organ is or whatever the odor is, right, it has to come out being somewhat of a sparse sugary representation. It doesn't have to be super sparse, but it has to have the right properties. It does have to be encoding some real feature of the world, and it has to have a sparse application. And so Gabor filters are good example. It works pretty well.
Yeah, they use it in
I have what might be a naive question, but I'm curious. You mentioned during the talk, I think it's your talk, that you modeled neurons and the connection between them. So I'm wondering how you chose how far down the stack to go. Like, you're probably not modeling atoms.
So I'll tell you. So
It's not a naive question. It's a good.
So
really good question.
almost all artificial neural networks model neurons as a cell body with some number of synapses with weights. Okay, and they're usually not that many. Sometimes some few, 3 or 4, some go up to some dozen, but that's what they are. We go a couple steps further than that. First of all, it's now known that it wasn't known 20 years ago, but it's now known that the dendrite, most real neurons have thousands of synapses. Not 20, not 50, not 100, but thousands, so 10,000. And we also know that on the dendrites, the dendrites themselves, these are the branches coming off with all the connections are. No, actually, no connections are off the cell body. There's no side of it. They're all in the that the regions of the dendrites are separate processing units. They act like coincidence detectors. So a small section of dendrite actually if enough inputs come in at the same time, they're active, it will generate a dendritic spike, and they'll have a large effect on the cell. So there's like a 2-stage cell here. It's like there's a cell that's the body itself, which generates the output, and then there's dozens or hundreds of these dendritic segments, each is doing its own process. It's like a 2-level network. So this is well known. Although I only know one other model in the world that takes advantage of that, and it's a very primitive one. So the CLA takes advantage of that next level processing, which is almost, in hindsight, it's so obvious you have to do that. Because, real brains have thousands of synapses. You have to have some explanation for it. Now we have an explanation for it. Why it's doing it. The other thing we do that's a little different is most artificial neural networks, the synapses are some weight. And in training, as you increase the rate, you decrease the rate. And in fact, most of these have very precise weights. A lot of these networks, we go from 2.467 to 2.492, whatever. In real neurons, synapses are stochastic. They're very unreliable. They don't always work at all. They're just totally unreliable things. And so any kind of biological theory can't require any precision on those. But we do also know something else, is that synapses grow very rapidly. They form new ones. And so I read this someplace many years ago, 3 years ago. I don't remember where I read it, but someone said, learning in the brain is really not about strengthening synapses. It's about growing synapses. And so, going from a 0 to a 1 connection is far more interesting than going from a 2.2 to 2.3 connection. And so that's how we model it. We model the growth of synapses, which is another dramatically different thing than most neural networks. I mean, we know that's true of biology now, and it makes a lot of sense from the information theory. So when we train, we start off with what we call a pool of potential connections. So a cell can make a lot of potential connections. There's a lot of things it could possibly connect to. And as we train, we sort of start growing the spine, the synapse. And at some point, we call that the permanence. At some point, we say, oh, it's made a connection. Now we call it a 1. So it goes from 0, 0, 0, 0. But the synapse with permanence because of the growth. So the two major, those are two major differences. We don't go below that. We don't go down to like ion channels or properties of morphology of the dendritic branches. So those are the two big things we do. And the other thing we do is we have cells can predict the state or an active state. The predictive state is essentially just in neurons. It's a depolarizer. It's a cell that has its internal voltage has been raised a little bit, but not enough to generate. And that's a predictive state. So those are the three big things: the depolarization versus the dendritic properties and the growth of synapses. And that's as far as we went. We didn't need to go any further.
I guess my follow-up question would be like, okay, if you can represent this system, this immune system, it has all the properties that the brain has itself. What's stopping you from just like doing the brain? If you can model this act.
So just go by analogy, go back to 1950 and say you were a very impressive young person who said, I can see how this is going to work. We're going to have these, these really super fast CPUs with multi-cores and stacks and cache memories and super fast high density disk drives. None of this existed, right? And we're going to have these super high level compilers and all these development tools, none of which existed. And then you say, well, what's stopping us from building that supercomputer in the future? Well, we're still back in 1950, and none of that stuff can be built, and we never built any of those things. We have ideas how they might be built. My point, I'm trying to give you a sense of where we are, right? So there's a lot. First of all, there's a lot of things we don't. Even if we have inklings about how this is supposed to be done, there's a lot of things we haven't done yet. There's going to be issues and problems. And
there's a lot of engineering challenges.
A lot of engineering challenges, like how do you get this to work, and what's problems going on here? I mean, we run into this stuff all the time.
In some sense, that's why you're releasing it. To enable a lot of people to work on this and go through a lot of that to create this.
So conceptually, it doesn't seem that hard, but from an engineering point of view, there's a hell of a lot that needs to be done. And as we said earlier, this stuff is too slow. You need custom hardware. We have none of that today. But it's something to bear in mind that neurons are really slow. They only run at a clock cycle about 5 milliseconds. The neuron can't do anything faster than 5 milliseconds. We can run things in silicon a million times. So in theory, we should be able to build brains that not only bigger, but a million times faster than, But, we're talking, probably some decades.
But in those 5 milliseconds, the neuron is doing a heck of a lot of computation.
Yes.
It's going through the 10,000 synapses, and there's lots of nonlinear stuff going on.
Well, that's an engineering problem. That's an engineering problem. But, in theory, and if you put your 30-year hat on, I know there's no question in my mind that we'll be building machines that are bigger and bigger and everything much faster. So conceptually you can see that, but it's something.
Yeah, and the question is, do you want to make a human brain, or are you happy with really smart learning pieces of silicon that do your bidding?
Yeah. Well, I think just like in the computer world, in the computer world we have lots of microcontrollers that are embedded everywhere, doing all kinds of stuff, and then there's really big CPUs, and there'll be a world like this too. There'll be lots of embedded little,
it's kind of the same argument. You want a humanoid robot, or are you happy with one that makes cars? In the dark.
So I think we'll do all, right? Although I'm not a big fan of doing humanoid. I think that's a little bit of a red herring. A lot of people are excited about that, but I don't think that's really what we think.
So what are your thoughts on the Blue Brain and European Brain project, and do you think that will inform any of your work in the coming years?
Well, there's several large-scale brain things going on. Blue Brain is an IBM initiative, and Henry Markov and Brokoff, now they're doing the Human Brain Project, and then now recently the U.S. government announced the what's it called? The Brain Initiative. That's right. So I actually don't know what's going on as much with Blue Brain these days. I know a little bit more about the human brain, but I don't know.
Are you hopeful that the stuff from
Well, no.
Project will
So
inform?
the guy at IBM who does the Blue Brain project is Yoda, a very nice guy, and when I spoke to him a couple of years ago when they were doing this, they had these amazing simulations of all these cortical column, all this detail, going down to this discussion really going down to machines and so on. But they had absolutely no theory. There was zero theory about what it should be doing or why you would do it this way. And it was like, just put it all together and see what the hell happens. I don't think they've moved away from that, but I don't know that. So and the Human Brain Project is the same thing. They have absolutely no theory about what it's supposed to do, why it's built this way. So, and they justified it by saying this will be sort of a test bed for testing ideas and testing disease models. Maybe I don't know, maybe it has to. But they're very different. They're starting from very different assumptions.
But are they unanswered questions you'd find useful that you think those sorts of projects will answer? Or do you think it's still so detached from?
I think it's so detached from the theory, and there's no point having a completely high fidelity brain the size of a rat if it can't do the simplest things that a rat can do. It just, I don't even know where to start.
I think
all the questions about hierarchy and sequences and language and all of that, none of that can be answered.
So we're much better off asking questions of neuroscientists because there's some real data there that we can use for. And in fact, there's tons of data that already has been. We've used a lot. Almost this whole thing is biologically derived. So there's a huge amount of neuroscience behind what we're doing. But there's questions that I have that would help going further. And as far as I know, the people I've asked about this and the literature circuit down haven't found answers to some of these questions. Some people just haven't even looked at it. It's very, very, very difficult to get data from neuroscientists, anatomists, and physiologists to medical workers. It's an incredibly difficult thing to do. So it's not so easy to go into some neuroscientist's office and say, hey, by the way, would you do this experiment to, tell me how these thalamus cells work? And they're saying, that would be 4 years of my life, and I would have to direct my entire life to do that, and I would have a 30% chance of success. And so it's not like, hey, look this up and check out your mouse there and tell me what the answer is. So
the debugging cycles in neuroscience are way longer than
it's an incredibly difficult science. So we're very, very thankful that all the work that people have done over the decades. I still find research that was done 30, 40 years ago useful because it's just been unassimilated into theoretical theory. So there's tons of neuroscience data that's just sitting on the shelf. And the trick is to go find it. And when you're looking for something, it's usually something there. It's got the data.
So kind of a related question, are you happy with the CLA the way it is right now, and are you going to kind of move down the path of commercializing it or moving it out so it works better, faster?
Well, I'm thrilled with the progress we've made. There's no question about that.
Well, I guess where are you going to go next?
But obviously, it's just
applying
the beginning. It's just the scratching the surface. There's some fundamental questions about the CLA we'd like to answer that we haven't answered. But then, really, most of the work has to do with integrating it into regions and adding low exception motor and talking about attention and talking about that at all. Building this into the sheets, making it fast, building hierarchies. I mean, there's a hell of the decision. If you're trying to talk about decision-making processes, like what evaluates what actions it's going to take, that involves something called basic angle. So there's a lot of stuff that has to be done here. But I think the CLA is going to stand the test of time in its basic form. I don't think it's not going to be thrown out. It'll be tweaked a little bit. But, from a theory point of view, I think it's going to stand.
Yeah, I kind of liken it to, I mean, if it is correct, figuring out the shape of a wing, and it's like, well, we don't need to put feathers on the airplane, but maybe we need a bigger engine.
Yeah.
And materials.
Yeah, to understand the principles of aerodynamics, right? How wings are involved in that.
Yeah, I think it's a great idea. So once you have the basic idea of aerodynamics of the wing, well, you can improve upon it. We're still doing that.
Right.
Now we're doing it, putting little things in the hands and all that stuff. But then there's materials and making it better and adding the fuselage with lower weight materials and
Wi-Fi
it's just-
inside.
Yeah, extending the analogy is probably further than it should be, but the Wright brothers understood the aerodynamics principles and some basic concepts.
Yeah, and they studied birds quite a bit.
Yeah.
Well, but along the lines of those analogies, they realized that we were not creating birds.
Exactly. Yeah.
So when you're modeling the human brain, have you found inefficiencies in your model because it's based on the brain? And have you left them in on purpose or created different?
Well, there's a lot of things we didn't include because we think they might not be important, and they might be red herrings. I'll give you one example for those who know something about brain. There are various rhythms in the brain, curves, during wakefulness, and sleep periods, and so on. And so these rhythms occur. People study these extensively. Like what happens to these rhythms? Like you can have massive cells, they're occurring firing at the same time. And some people think this is what brains are all about. That these rhythms solve these fundamental problems. We don't think so. We think the best hypothesis I have is that these rhythms are solving plumbing problems with biological neurons, and they're not essential for information theoretic purposes. That's my best guess. We don't see a need for them. But I can postulate why real neurons need them. So we wouldn't include those because it's like don't include ion channels, don't include mitochondria, don't include blood vessels. It's not necessary. So there's a lot of people who didn't do it, and some people will take objections from it. If you study these rhythms, you simply let that come up.
And those rhythms are really one of the only things that people have observed in the large scale spike-making.
Yeah, so you put the little EEG skull cap on, and that's what you're going to see, right?
Right. And then the simulations, that's what they're looking for. Same kinds of synchronous spike.
Yeah.
And what about gas nets? Those look promising for a while. Gas diffusion models.
Yeah, I've heard of them. I don't know
what it is. Is that a neural thing, or is that
It's the idea that the neuron, it's diffusion of gas from a neuron. You put your neurons in your model on a two-dimensional grid or a three-dimensional space, and then a neuron will, instead of just directly communicating through synapses, they also, when they fire, will diffuse a gas that ends up deteriorating from the square of the distance, and can cause an inhibitory effect on neighboring neurons in the space, or an excitation in the surrounding neurons. And there were some interesting studies a few years ago with the gas diffusion nets. That there was actually at MIT they had a little plane that could fly itself, go in and out of doorways, down hallways, never hit a wall, and it had evolved through a genetic algorithm for neuron placement and things, and it only, when they took it apart, the evolution had built this very complex behavior and only had 9 neurons in the system. So there was a lot of excitement around that a few years ago.
Yeah, that could be great, but it's not the brains. Brain doesn't do anything fun.
Well, it has more complicated problems.
There was a paper in Nature 10 years ago, and I know the author was so excited about it. And he was modeling a major feature in the neocortex of 3 neurons. And and these 3 neurons exhibited the property that you see in the cortex in certain cells. Neurons did not. Brains lose neurons left and right. I mean, they're unreliable things. Anyways, I'm just saying it's a very confusing space. You can look at that and say, hey, look, we evolved something. But, there's a lot of techniques that might work to solve a particular problem. And it's not the disto, it's that learns in how large-scale brains work. How you build real complex models of the world and understand everything. And that's not going to happen with simple things like that. And I don't know anything about the gas diffusion stuff, but it seems like whatever it would be a fairly slow mechanism. I don't know if that's true or not.
It was able, the studies they did on it was interesting because it was able to turn off large sections of the neural network when it got particular inputs. So an excited area of the brain could actually turn off surrounding areas.
There's a whole series of stuff about brains, about these neurotransmitters that are distributed broadly, to do with emotional states and learning rates and so on. We don't model any of that stuff. If you're trying to say we're not trying to build an emotional being, and learning to be pretty simple at the moment, turn the switch on, you learn, switch off, and stop learning. Anyway, this is an example of all the trade-offs you have to make. There's a guy with a theory that the information processing is happening in the blood vessels. And he's got evidence to show that blood vessel growth actually is part of learning. Maybe it's true, but they do a lot of weird stuff. It goes in all kinds of bags, tricks in his bag. We're looking for well understandable information processing means that fit the vast majority of what we know, that brains are built with billions of neurons with connections in this hierarchy.
I think there's a lot of stuff we've left out, but by modeling the biology closer, there are also a number of computational properties we gain that we have difficulty doing any other way. So if you look at sparse distributed representations and modeling the dendritic structure of neurons and how they're connected in a laminar structure, we're able to get really powerful sequence memory. We're able to do sequences and variable order sequences. We can the temporal pooler is an extremely powerful temporal prediction engine. So you can make, because it uses sparse distributed representations, they can make sort of multiple predictions simultaneously, multiple steps into the future. And that's really hard to do with the Bayesian theory and with the traditional theory.
Yeah.
Another property we got just sort of pops out of it is just the continuous learning. Just the way that the synapses are updated and the way it learns naturally through the data is, you get online learning and continuous learning, and it sort of comes for free. Again, that's something that's very difficult to do in kind of the batch machine learning. So I think there are some computational properties we really gain by modeling the biology a little bit closer. Not that we would have to do it that way, but
we didn't start that way. We didn't say, let's build a model that uses dendritic properties. It wasn't how we started. We started with a set of theoretical constraints and then said, what in the biology do we need to do this and do it? But I think, sometimes makes a great point. What gets us excited about this is not that we've solved a particular problem, like training some robot to do something. It's that we solve a set of theoretically very, very difficult problems that fit together in sort of a holistic whole and a large-scale theory, and that set of constraints is very difficult to satisfy. It's just, we tried for years. It's really hard, and when all of a sudden they all fell together, one fell swoop, it's like, oh my God, everything works. All of a sudden, everything works. All the problems are solved. And, so that's what gets us excited more than like, we beat somebody on some benchmark doing something. It's more like, it has to be some validity. When you solve a lot of constraints simultaneously, there has to be something to it. It's very, very difficult to do.
So, I guess since you're not working with benchmarks, how well is this working in the real world? And also a couple other things about how many steps out can you predict, and what are the factors that go into allowing you to predict out further and get this explosion of memory?
Those are two separate questions, actually, totally separate.
Yeah.
I think that predicting steps into the future, it really depends on the data. You can predict arbitrarily far if it's a very repeatable pattern. If it's a sine wave, I could predict a million steps out into the future.
By the way, we do a non-biological trick to do that.
That's true. Yeah.
I don't know if it's worth talking about that, but as I said earlier, you can take the state of the CLA, and that's everything it knows about the world at that point in time. All past history plus current activations. That sparse activation of those 64,000 cells tells you everything there is to know that this system knows. And so when we want to actually predict multiple steps in the future, we do it via a separate classifier, separate classifier actually. It was the most expedient way of doing that. We take that state and we just reclassify those points. So that's an engineering shortcoming of how we just did this. So now we can do things that brains can't do. We can predict multiple steps at the same time, multiple places in time, whatever we want to do, whatever the problems the customer wants to solve. The other question was about, what was it?
How well is it doing in the real world? Applications. Based on the other software choices that you have out there.
We spend a lot of time on this, and we still don't have a great answer.
How do you prove it to your customers? You're going to go get a new customer and say, hey.
Well, typically customers have some of the same.
Yeah, and I guess there are two types of
That's
customers.
your benchmark.
Yeah, I mean, there's some types of customers that have existing methods, and you can fight on there. Either you do better or you don't. In cases we do better, and in cases we don't. But there are also customers that don't have those benchmarks, but they don't have any existing. They don't have a solution outside.
There is no tool.
Yeah, but they need they need a system that can handle streaming data, that can adapt to changes and deal with and roll
So
it out.
when we talk about the value to a customer, this is getting off the science, like a business proposition. The value is automation in online learning. We don't say, oh, we're going to beat every algorithm we got. We say, we can build 1,000, 10,000 models very cheaply. Each model will be individual to the thing you're modeling. So if we're going to do 20,000 meters, each one will have its own model. There won't be one model that we're applying to 20,000 meters.
Weather stations.
Whatever,
Yeah,
right?
yeah.
So that's the first prop. Those are the two propositions. We can do 20,000 models, and each one is learning independently. By the way, you can't have any way you can get a machine learning person to do that. So that's the value proposition, as opposed to, oh, we'll beat your 4 PhD machine learning scientists on this particular problem. We probably won't. You put enough smart people in a room on a particular problem, they'll come up with something. So that's not where we shine. We shine like, let's automate, and let's automate the entire process.
So there was a description earlier today that showed your prediction of electricity usage. Can you say, and this is maybe repeating the last question, can you describe practical ways that this algorithm is being used?
So that particular one was this guy down in Australia. And just back to the previous question. He had spent some fair amount of time trying to do those predictions, and we, in a very, very short period of time, he did better than he was able to do. So he was very happy about that. The deployments we have today, I was talking to someone else earlier. I can't go into all of them, but basically we've had the most success in closing customers. We have one big customer in the energy space. In fact, they're on our website, it's Aeronaut. And that's the furthest one we got along. We have a whole bunch of these things that we call POC, proof of concepts that are being involved. The problems we're running into in the business, and I don't want to get too much into it, have less to do with the algorithm and the value proposition. It has more to do with, are people actually able to do the automated modeling? Does the rest of the infrastructure in place? Are they actually able to get the data and stream it to drive? Well, just get it reliable. The encoding part's not too hard. It's just that the data. I'll give you an example. So we did some work on windmills, modeling windmills. It looked pretty promising, but in the end, it actually turns out that the windmills are offshore someplace in the North Sea, and the data doesn't. The person we're working with doesn't get the data. The data goes to this other center, which is owned by the windmill. And they don't want to give the data away because they think it's valuable. So, trying to get like, okay, let's just take all that data and stream it to Grok. Well, it doesn't happen. There was other problems associated. The issues we have. So, look, we're not a profitable company. We're small. We have only 2 deployments. But we've had a lot of, we've had a lot of validation of the algorithm. And our business issues are not related necessarily to the algorithm. Related to other things we're solving. I don't want to get too much into that because it's not about.
Do you think it works better with discrete data, or is continuous data just as effective?
Yeah, we can handle both types.
Well, just from a practical standpoint, I'm working on a project right now that's using motion software. It does facial expression recognition, and it puts out a steady stream. It's not just happy, sad, disgusted, but it's a continuous stream. And
it's a distribution, or is it a stream?
It's a stream. So we'll be recording that time-coded using, well, actually what it is for a university. It's a research project, and it'll be recorded while students are involved in synchronous video instruction. And so there will be real-time feedback to the professor, and I won't get into the hypotheses, but this will happen during instruction. We're not planned, originally, there were no plans to actually record the professor on video. But after what you said this morning, I got to thinking, if we did that, would it be possible for us to actually predict student reactions from what the professor was doing. In other words, we have the professor's emotional, tracking the emotions of the professor, emotions of the students.
You want to predict the students' emotions?
Right.
And do the emotions change rapidly? How often do they change?
We don't know yet, but just constantly. And
So if I could measure, if I could take a reading off the student, would I have a single variable that says, or as a category, or would I say, oh, there's a scalar value for happiness and sadness, and what would it look like?
Actually, when you plotted, if it was for a given student, if we had sadness, it could go like this.
I'm just saying, like, you have separate variables for sadness and happiness?
And happiness could go like this.
Okay, so there's multiple variables coming out at the same time. So that, if it's changing rapidly enough, that might be a very good problem. No?
Yeah.
You know, if it's pretty static, there's not much to look for. But if these things are actually changing throughout, in the order of minutes and so on like that, that would be a great problem. And you say, well, my job is to predict how sad the student is. That'd be a great problem for the CLA. It would be if there's any patterns to how the students do that. If they kind of go through any kind of cycles and so on, they'll discover that. If it's just random, the student just is a random emotion generator, then we won't find anything. Maybe teenagers, that's what it is.
You're even listening to the professor. That's
another thing is if you had some metric on the professor, that was also another variable. You could tell, at least with Brock, well, in the CLA, you basically feed that into and say, well, does that help predict the student's emotions? So maybe when the professors are animated, then students have a certain sort of behavior, and when the professors are not animated, the students have a different sort of behavior. And if there are structures to that temporal data, then it should discover that. And it'll give you back a prediction, as Scott was showing earlier today, and it's sort of a distribution of like the prediction is like some percent this and some percent that. Just question me. I don't want to know that. I was thinking the same thing.
This is brand new software, and it was just commercialized. What happened was a couple of years ago there was a one and only one worldwide conference on facial expression recognition, and there were 7 universities involved that actually produced something that worked, and everything worked, but not really well. And what they did was join forces, and so it became available at the beginning of this month.
Right. So there's a question of the quality of the data.
Right.
I know that facial recognition is great if you have like nice frontal.
So, what if your encoding space is actually noisy?
Yeah.
So, but not noise. It was noise again, but it was just somewhat noisy. The CLA would still would work.
Yeah. It's pretty. They're claiming 200 man years of development in this. It's built on. It was actually built on the solar system. Okay.
Well, they're learning. Critical learning is going on.
Yeah.
Okay.
And I've seen it in action. It actually works.
Okay, but let's say it was noisy, right? A lot of the data we look at is noisy. There's an underlying cause, which in theory is some sort of pure Platonian thing going on out there, and then there's some real noise on top of it. But as long as the noise signal ratio isn't too bad, the CLA will still learn. I mean, you could show it, for example, we didn't show this, but I'm pretty confident, if you like that song example that Scott and Matt showed earlier today, if you showed it noisy versions of that song, or the noise was randomly dispersed, it would still learn that song. It would take a little longer, but it would learn it. No question about it. In fact, it would probably learn it even if there was a lot of noise, as long as the noise was less than the signal at some point, So it doesn't matter how long it takes to learn and so on. So I think even a not-perfect emotion encoder would be okay as long as it wasn't wholly random, and then there's some relation to reality, it would be okay.
Well, I kind of always suspect that things that deal with niche vision stuff, because I've read a lot of papers on all these techniques for like finding objects and images. Well, someone had done a study, and they always came out with these beautiful 95% accuracy. So someone did a study and found out that they only got the accuracy on the images that they used. When they used it on some other set of images, it's looks like totally blown out. And it turned out it wasn't looking for the objects and images, it was just looking for certain really weird anomalies.
It overfit to the data.
Yeah, like in the background or something.
Overfit.
So I always kind of get suspicious when someone, because they put some data and they got really good accuracy.
Is that a problem with the CLA? Does it overfit in certain cases?
Yeah, I was talking about this thing. Supervisor is more than machine learning expert than I am. You just kick me.
Sure.
If I say virtual kick me, okay? You know, the concept of overfitting is it makes a lot more sense when you have like a training set and where you say, okay, I'm going to learn and like I take a training set and I learn the patterns of the training set. Well, then I run the algorithm on that training set again. Well, I learn the noise. It doesn't really matter. I'll overfit everything for it. With the CLA, you can think of this way. There's a so let me give you a sort of a little flavor. There's one of the parameters is how fast it learns, right? How quickly, you know, we could have made that song thing learn really fast, like just
changing what?
Changing how quickly the synapses form. Okay. How many times
we could have done it at one pass.
The threshold of
how quickly? How many times do I have? If I'm growing a synapse, how many times do I have to reinforce it before it forms a synapse?
Which parameter?
It's a learning rate.
Permanence.
No, increasing the permanence. Okay. You go from 0 to 1 permanence in one flash,
Okay.
you're done.
There's an initial permanence that could be instantly.
Yeah. Okay.
So what's the advantage and disadvantage of fast and slow learning? Fast learning is great when the underlying causes are changing very rapidly. So anything new that comes in, you assume that's important. And you want to pay attention to it. So, but what if you have a lot of noise in the world, and you don't know, the system doesn't know when you have a new pattern whether it's just noise or if it's the beginning of a new pattern, right? So if it's the beginning of a new pattern, you want to learn very quickly. If it's noise, you want to learn slower because otherwise you'll learn the noise, and the noise is not going to repeat. So in that case, you're overfitting, but the results will be lower accuracy. It'll just be, it won't do as good. It won't. We will overfit to the data, and our result will be less accurate at future data.
Okay.
So in most usually overfitting, you have a foolishly high accuracy because you're working on some prescribed data set, right? Anyway, okay.
So do you learn and forget the same rate? I can't remember.
Yeah, they tried to get it. Right now, the learning rate, the learning and forgetting rate are tied together. Right. So if you learn faster, you forget faster. If you learn slower, you forget slower.
And
so here's another way to think about it. What if I saw something 4 times last week, and I saw it 1 time yesterday, and they're conflicting, right? Which do I pay attention to? Do I pay attention to the more recent one that I've only seen once, or do I pay attention to the thing that was 4 times last week? There's no right answer to this question up front. There's no a priori right answer. It has to do with we don't know. It's physics of the data. So that's why the learning rate is a parameter. If you have a very noisy data set, the learning rate should be better slow. Just like let's learn slow, make sure we get to the patterns here. If you have a very, very clean data rate, the data like that song was a very clean song. We could have just learned it just like that because there's no noise in it.
So as you've gotten experience with customers' data, are you kind of parameterizing like kind of range of learning rates, kind of max, and then I'm interested in hardware implementations, and one of the things I'm interested in is how many bits of precision permanence has to have, because it makes a big difference. There's a lot of storage of permanence in the CLI.
We have a range of parameters that we work with, and we found that for most problems, it's just fine within that range. Where exactly you fall in that range, we tend to do this optimization process.
Right. So let's talk specifically about the permanence. The permanence goes from 0 to 1 by 0.1. We've never done anything else. I don't think we've ever done anything else. So basically, there's
very coarse.
Very coarse.
So like 4 bits.
Well, I guess you could do it in bits. We don't do it in Office. We don't do it in Photoshop, right? We do it in Office.
No, I know, but
we probably use a 32-bit image for that.
I don't want to get any other answer.
It's a floating point.
0.1.
Okay. The learning rate actually, it also is not a very big dynamic. So I don't know what the actual numbers are, but it's probably like 3 or 4 sets. I don't know what.
Yeah, I think that's just fixed.
We don't even learn on the learning rate. We just.
Okay, so you mean the increment?
Yeah.
Yeah, I don't think so.
Yeah,
I think we changed the initial permanence and where
Oh,
we connected, and that's.
Okay, where you can. Yeah.
So those are values you can change, but you're saying we don't currently.
I think the increment we don't typically. They're all kind of interrelated, so usually you don't have to change all of them. You can keep one fixed.
The things we actually spend the most time determining are what's the best encoder for a particular number, and then also that's like evolving a retina. Like, well, what's the best retina for this problem? You know, and then also we spend a lot of time deciding which factors help you contribute to it. So like if someone gives us, here's 20 variables, and I'm trying to predict which of those other 20 variables help. Then that's not something we have to permutate over and figure out.
How does that process happen? It doesn't happen in CLA.
No, that's part of the swarm. That's part of the optimization.
So what we do is we have a process where we walk through, we try each pairing of factors, and then we pare them down, and try pairings of those, and then the other parameters are tweaked using this part of the swarm optimization thing where you set each set of parameters is like a point space and kind of move towards the best one at the point in time. And so we'll run, in the swarm, we'll run like 30 models at a time for a little while, and then we throw some away and create new ones, and then eventually we sort of settle in and say, okay, that's good.
Do you ever see this becoming not something you do up front, but actually as part of the CLA?
Yeah, well,
based on the data that's coming in, the results you're getting, part of it tunes itself. Yeah.
Well, you talked about the dynamic thresholds. Right now, the thresholds, but not here. But sorry. Right now we fix the thresholds and we sort of, but it might be dynamically set.
These are thresholds of the encoder, like, are we
the temporal Pooler threshold.
Oh, those temples. Oh, yeah. Oh, yeah. This is the dendritic segments. It's pretty deep. So like the dendritic segments have how many active synapses have to be active at the same time to generate the dendritic fiber state, and that is something that's dynamically controlled in the brain, but we don't do it dynamically. Yeah. That's the idea here. The example I always use is like if I tell you look at a cloud, you don't see anything, and then I say, well, look at the cloud, tell me what you see there. What's an animal you're looking for? So you see an animal there. Well, there isn't an animal in the cloud. You don't see an animal in the cloud. So why all of a sudden do you start saying, oh, I see a dog? Why is that? But I think what's going on there is that the temporal pooler and the dendritic segments are not really matching. They're not really. It's nothing good enough. And then it says, well, this is lower the threshold. And so something comes out. Something will pop out. You lower the threshold enough, and we'll just start matching that. Okay, what's the best thing that can match this? But yeah, we do these all the time when we're looking at a problem, trying to solve it. We're saying, "Oh, this is a hard one. What is that?" We don't do it. So, but these are all things that could be enhanced. If you do this in the open source community, it'd be great. That'd be very interesting.
I'll make sure.
Okay, so can we use your solution approach applied to, say, today, the last, say, 90 minutes? Meaning, this may be a long question. So if we record a session, we play through this model, and just like each one of us.
You talking about this recording up here?
Yeah. So
that's a video recording. What's it going to do with it?
Yeah, I mean, or audio. What kind of input you can take and say?
Well,
so what I'm getting to is that each one of us at the end of the session has our own impression of what is happening, right?
Yeah.
And as in happen in many cases. So, but if someone actually transcribed the whole process, let's say tomorrow or next week, you read it. Say, oh, this actually would happen. I missed this.
Actually, even if it was transcribed and we all read the exact same text, you'd still.
Okay, good. Yeah. So it'd be nice to listen to a quote-unquote objective computer, tell us what's actually happening.
Here's why that would fail.
Yeah.
And maybe this is a good thing to kind of Here's why this failed, because your interpretation of that is based on all your prior learning. Your prior learning is different than my prior learning.
True, yeah.
And so the words, I'm amazed by this, but people have absolutely different understanding of the same words. And sometimes you get these conversations and we're saying, oh, talk about prediction, they're talking about prediction. We're actually talking about something completely different.
Yeah.
And I see there's a lot going between like neuroscience and machine learning and data science. So my point is, the objective, how you perceive it is not in the data itself, but it's in all prior knowledge.
Yes, knowledge, right? So the modeling process, there's no way of factoring into the knowledge.
So the computer learns like using a future brain and CLA type of thing. It would have a different interpretation than your knowledge.
It's unsubjective.
It's also because whatever it's prior learning.
But the computer's been trained by lots and lots of different bots that have happened in this room over the past 10 years. It's possible that it could come up with some recognizable pattern, if there is one, in the timbre and tone of the audio.
Maybe. I was talking to this guy from Brazil. He was telling me about that. He's reading these support requests written in English, but if they're written by a Brazilian whose native language is Portuguese, an English speaker who grew up in English cannot understand them. But they're written in English. so what's the reality? I don't know. I think we have a long way to go before we change this.
But you guys all sat here for 90 minutes and listened, so it must be interesting.
I do wonder if our use case would be setting up alarms and having you distress.
Where's the data coming from?
Streams of medical observations. So setting up an alarm when a pattern changes, like a drop in frequency or a raise in frequency at certain times as well. Is your system tuned for that kind of?
It all depends. That's a perfect example. That's a little bit like did you see the afternoon talk with the windmill? Okay. There was an example we were showing with data from oil. And it was the data is going up and down very rapidly, and we were able to detect it. This is something we do very well, actually. We can detect anomalies that are not threshold things. They're more like it's more like there's a melody coming in, and it's very noisy. Melody snippets. This is the melody snippets. And all of a sudden, the quality of those melody snippets change. The melody changes. The notes are not wrong. It's not out of range, but all of a sudden it sounds different. And it's a very difficult problem to do. We don't know of other solutions to do this. Normally, we don't know of anyone else to do this. But that, we can detect it, and we do a good job at that. And so that seems to be a very promising area for us. Now, the trick is you got to have real streaming data. We were talking to one company where they had medical instruments, and these instruments were in the hospital, and these were like the things by your hospital bed. And they were streaming data all the time, every, 15 minutes or something, literally back to the home office. So there's like a constant stream of data from everything. That's a perfect example. We could look at that and say, this thing is an anomaly. If you're looking at medical patient records, you've got like, I've got millions and millions of records, and they're coming in all the time, but you only have 3 records per patient. And that patient, one record 2 years ago, one record 2 months ago, one record. That's not good data. That's not really, even though you're getting lots of data in the stream, it's not I can't feed that to the So just to be aware of what. There's 2 extremes. One is a great fit, and one is not a good.
So you need some semantics to understand the purpose of the data.
No, not really. No, we don't even know what the data means. We could care less. We just tell it's a number or something like that. But what you do need to know, the data has to have, to do the kind of the anomaly detection I was talking about, you have to have a real high velocity stream of data. You got to have a lot of data points coming up. It's got to be a real stream as opposed to a lot of data is not the same as a lot of data points over time. I mean, if you're modeling a patient as opposed to everybody, a patient, I have to have a lot of data points for that patient. Typically, they don't have that.
I'm thinking more in terms of a facility, even though it's far from the patient, the facility itself is one of the.
If you have a lot of data from the facility, let's say you have like how many people. Let's like make up something. I mean, how often this door opens on every floor of the hospital. That's something interesting. I didn't piece of data. That would be great. We could model and say something's unusual happening on floor. You know, that would be good.
That's basically the kind of thing. So you have multiple hospitals coming in, you want to see which hospitals have the most doors open.
Well, if something's anomalous, again, if something is happening on a regular basis, you know, it's not once every 2 days or something like that, but it's every hour or 15 minutes, or every minute, then that would be a good thing. So yeah, I'll learn these patterns, you know, just throwing things, these things are changing all the time. It would be good.
So it doesn't have to know this, you don't have to encode semantics in your data, is that?
No, it's just a number, it's a number. If it's a category, it's a category.
But the category has a semantic meaning.
Well, actually,
Yeah,
right.
categories.
So let's talk about this briefly. So today we do numbers and categories and dates. You could build custom encoders like we were talking earlier for like words. So we don't have that. But a number, we don't really need to know what the number means. We don't even know what it means. It's just a number on a number scale. We're going to represent it, and we turn it. We have a generic encoders which turn it into a distributed representation, a set of bits, where each bit represents a overlapping number range. So if I have, maybe I have 100 bits, and it's representing a number line, and you pick 24 as the actual value, it'll intersect a bunch of ranges that are overlapping with 24. So I'll have a lot of zeros, and then I'll have a bunch of ones and a lot of zeros. That is a sparse encoding with semantic meaning. Each bit means something. And so if the number changes from 24 to 25, the representation may lose a bit down here and gain a bit up here, so the two representations are very similar. These two are very similar, 24 and 25.
Digital sliding scale.
Maybe, something like that, right? And when we do categories today, you could do what we do is do something very simple. We generate a random sparse distributed representation for every category. So we say there's no semantic meaning to these categories. They're just independent things. This is A, that's B, but there's no ordering to them, there's no meaning. You could do a semantically encoded category coding. You could say, well, I know that, you know, pharmacy is similar to a drugstore, but it's very different than a supermarket or something like that. And you can code them different. We haven't done that yet, but you could.
Well, and that's kind of like that map that I saw on the site that you mentioned.
Yes. They did that for words.
It's a semantic encoding of bits.
And then we take dates and times, and we also do a very simple semantic encoding. Okay. We take a date and we say, oh, is this weekend or weekday? Is this day of the week or day of the weekend? Right. Things like that.
So as building an encoder, you could come up with your own semantic meaning, but CLA doesn't really need to know that.
That's right.
Just to know that these are
just like your brain doesn't really know that optic nerve is representing vision. It doesn't know that.
Now, if I want to get a prediction in the future, though, I should get back out a semantic bitmap of all these things that mean something, right? Is that true?
I mean, from the temple pooler, you'll get a set of predictions that's in the same language as what the encoder is speaking. It'll be in the exact same language, and
I can run it back through my encoder.
Yeah, you need a way of mapping that back into the original values.
Okay.
So we're running over. Before you go, if you want an ebook of On Intelligence, leave me a business card. If you don't have one, you can write it on the back of one of my cards and just leave it.
I don't have an ebook.
Really?
I want it on my Kindle.
If you want a POC, take one of my cards. Have a sticker and t-shirts. Small, medium, large, XL.
And
yeah, that's fine.
Okay.
Thanks for watching.